Now this video is the continuation of close packed structures. So in the previous video we discussed about close packing in 1 dimension, 2 dimension and 3 dimensional close packing, where we placed a second layer on the first layer. Now next let us place a third layer on the second layer in 3 dimensional close packing. So next is placing third layer over second layer. Now, when you place a third layer over the second layer, we can place it in 2 ways. The first way is by covering the tetrahedral voids. So, under this, let's see how to place a third layer by covering tetrahedral voids. Now, we have the first layer as A type, second layer B type, third layer will be in alignment with the first layer, which means the third layer can be A type. Now, the next layer when you place will be aligned with the second layer, means that is of B type. So, here we get AB type of arrangement or AB pattern. And the structure that we get here is hexagonal close packed structure. Or the lattice that we get here is hexagonal close packing, hexagonal close packed structure. Now, example for hexagonal close packed structure atoms are metals like magnesium and zinc. They possess hexagonal close packed structure when we place a third layer on the second layer. Now, the next way of placing the third layer on the second layer is by covering the octahedral voids. So, this next is by covering octahedral voids. Now, we are placing a third layer in such a way that the octahedral voids are covered. Now, here the first layer is A, second layer is B, third layer is not in alignment with first and second layer, which means we have a different layer which is C. Now, only when we place the fourth layer, that will be in alignment with the first layer. So, we have here the pattern as ABC type of arrangement or close packing, and here the arrangement or the structure that we get is cubic close packed structure, cubic close packed structure, cubic close packed structure, or face centered cubic close packed structure. And an example for metals which possess this type of structure is copper and silver. They crystallize in this structure. Now, in both hexagonal close packed structure and cubic close packed or face centered cubic structure, you can see that each sphere is in contact with 12 neighboring spheres, which means the coordination number in HCP and FCC or CCP is 12. So, you can say that the coordination number in HCP means hexagonal close packed structure, and CCP is cubic close packed structure, or FCC. CCP and FCC are the same. Okay, face centered cubic close packed structure. What is the coordination number? Is equal to 12. So, this is about the close packing in 3 dimensions when we place a third layer on the second layer. First way is to cover the tetrahedral voids in which we get hexagonal close packed structure, and the second way is by covering the octahedral voids where we get an cubic close packed or face centered cubic structure, and the coordination number in both the cases is 12. Now, we will just see the coordination numbers in a nutshell. So, first we discussed in one-dimensional close packing. In one-dimensional close packing, the coordination number is equal to 2. Then, in two-dimensional square close packing, coordination number is equal to 4. Then, two-dimensional hexagonal close packing, the coordination number is equal to 6. Then, after that we have tetrahedral void whose coordination number is 4. Octahedral void, coordination number 6. Then we have simple cubic lattice whose coordination number is 6. Then we have hexagonal close pack structure, coordination number 12. Cubic close pack structure or FCC, face centered cubic structure, coordination number 12. Now one more we have, that is BCC, that is body centered cubic structure, that we have the coordination number as equal to 8. So BCC, body centered cubic structure, we have coordination number as equal to 8. So this is the coordination number of different types of close packing. Now next let us see formula of a compound. Formula of a compound and number of voids filled. Now we know that if we can get the number of octahedral voids, we can get the number of tetrahedral voids, because we know if n, capital N, represents the number of close packed spheres, we know that the number of octahedral voids will be equal to capital N, and number of tetrahedral voids will be equal to 2 times the number of octahedral voids. And in ionic solids, when I say ionic solids, we have cation as well as anion, and we know anion is larger in size than cation. These anions, they form the close packed structure, and the cations will occupy the void. And if the cation is very small, then they occupy the tetrahedral voids, and if they are large enough, they occupy octahedral voids. Now, if you know the number of voids occupied, you can write the formula of the compound from the number of voids, that is tetrahedral as well as octahedral voids occupied by the atom. We can write the formula of a compound. So that we can discuss with the example, 2 examples. I have written a question on the board. The first question: a compound is formed by 2 elements X and Y. So we have 2 elements X and Y. Atoms of element Y as anions make CCP. So we know that anions form the close packed structure. That is, and which type of close packing is this? CCP, cubic close packing. And those of element X as cations occupy all the octahedral voids. So cations can occupy tetrahedral or octahedral voids. Now in this question, the cations, they have occupied octahedral voids. What is the formula of the compound? So let's solve this question. Now let number of atoms of Y be equal to n. Why did we take atoms of Y as equal to n? Because it is Y that makes CCP, the cubic close packing structure. So let the number of atoms of Y be equal to n. Now if you get that number of atoms of Y, we get the number of octahedral voids. What's the number of octahedral voids? Number of octahedral voids will be also equal to n. Now here we don't want the number of tetrahedral voids. Even if we don't want, what's the number of tetrahedral voids? 2n. Now in this case, X atom occupy all the octahedral voids. So next, what can you write? All the octahedral voids are occupied by X. What will be the number of X atoms? Number of X atoms will be equal to the number of octahedral voids, which is same as equal to capital N. So you got the number of X atoms and number of Y atoms. Now you can write the formula of the compound, that is the ratio X is to Y. So what will be the formula of the compound? Formula will be equal to X is to Y, that is N is to N. So what will be the formula of the compound? X, Y. Now the second question. Atoms of element B form HCP lattice, that is hexagonal cubic packing or hexagonal close packing lattice, and those of element A occupy 2/3 of tetrahedral voids. So here, who will form the cubic close pack structure? Element B, because element B is forming the HCP lattice, and element A occupy 2/3 of tetrahedral voids. What's the formula of the compound formed by elements A and B? So in this case, let the number of atoms of B equal to capital N. Now, number of octahedral voids will be equal to capital N. Number of tetrahedral voids will be equal to 2n. Now, we know that 2/3 of tetrahedral void is occupied by which element? A. So A occupies 2/3 of tetrahedral void. Therefore, you can find the number of atoms of A, that will be equal to 2/3 into 2n, because atom A occupy 2/3 of tetrahedral void. So what will be the number of atoms of A? 2/3 into 2n, which is equal to 4/3n. So now you got the number of atoms of A and number of atoms of B. This is atoms of B and this is number of atoms of A. So now you can write the formula of the compound. Formula will be A is to B. A is 4/3n is to number of atoms of B is n, which is equal to 4:3, or the formula of the compound is A4 B3. This is the formula of the compound. Okay, so if you know the number of tetrahedral or octahedral voids occupied, we can calculate or we can find the formula of the compound. So with this, we complete our close packed structures. Thank you.